Hello everyone, welcome to this episode. I once stood at the pinnacle of the SIMA wave, holding the truths of fluid and structure in my hands. Everything can be simulated, the world is all about computing power. Platform mooring lines, jacket legs, waves and wind all rise and fall in the palm of my hand. 6 degrees of freedom fill the room, connecting heaven and earth. With a single thought, I can stir up storms and overturn seas. Using simulation as my mirror, I unravel the mysteries of sea and sky and observe the array of all phenomena. I make steel structures tremble in the void and let mooring lines dance within the data. I was born on the waves and bound to computation. People call me a SIMA creature. I am the offshore craftsman who has mastered the skills of G7 craftsmen. A quick note, this video only shares my personal experiences and insights on using CSOM during my studies and work. It aims to help PhDs in the field of ocean engineering better understand the relevant software so we can collectively contribute to the advancement of marine endeavors. This does not involve any cracked installation packages, internal materials, official tutorials for sale, etc. It is solely for academic and learning exchange and does not involve any commercial use. This video is unrelated to DNA and does not constitute official training. Alright, today, I'm going to share with you how to use the CSOM software to perform towing analysis. First of all, towing can involve one or more ships towing a semi-submersible platform, or towing a floating wind turbine, or even towing another ship or a net cage. No matter what type of towing it is, it always involves one floating body towing another floating body in motion, so the simulation process is generally the same. The first thing we need to clarify is what is being towed, which is generally a ship. It is connected by a cable, with one end attached to the ship and the other end connected to the floating body being towed, so we need to make this clear. We need to understand the relationship among the towing ship, the cable, and the floating body being towed. You can take a look at this simple diagram I have here. First, we now have two floating bodies. Let's assume that floating body 1 is towing floating body 2. Each floating body has its own red dot, which represents the motion reference point of the floating body. Then, the cable in the middle also has two endpoints. These two endpoints are also what we refer to as supernodes. Next, we need to clarify the relationships among these supernodes. For example, the motion reference point of floating body 1 acts as a master node. One end of the cable. The southern node is set with the attribute slave. You can also understand it as this end of the cable moving together with the floating body, meaning the floating body pulls this point along as it moves. Then, after this point moves, it pulls the cable along. Alright, next. The other end of the cable. This point is also set as slave, so who is its master? It's the floating body at the back. You can also understand it as this point at the back also moving together with the attached body because the cable is tied to this second attached body. So, we set the attribute of this point to 15. As for the reference point for the movement of the second floating body, it acts as a master, but its attribute is set to free, while the first floating body was initially set to fix. I will release it later on. After clarifying this hierarchical relationship, it becomes much easier for us to set things up. For example, the first floating body can move, which means this reference point starts to move. One end of the cable moves together with this point because they have a slave-master relationship, so this point on the cable starts to move. As this point on the cable starts to move, it will pull the entire cable along, and it will also drive the second point on the cable to move. At this point, the second point of the cable and the motion reference origin of the second floating body are involved. This is also a slave-master relationship, and this relationship can be mapped in both directions. In other words, if the slave point moves, the master point will also move. After clarifying this setup relationship, we can go into SIMA and try some random operations. According to what we've learned, I still owe everyone a theoretical tutorial. As for the theory behind SIMA, I will release a separate video on that later to focus on it in detail. I've been quite busy with visits recently. Alright, let's open the SIMA software. On the left side, let's create a new reflex scenario. Let's rename it to towing. Next, I need to create two waypoints inside. These will serve as our towing vessel and the object being towed. First, let's create the first floating body. For the first towing vessel, we'll use the Black Pearl from Pebbleton Jigsborough. It's towing Luffy's Going Merry. Alright, I'll name the first ship Black Pearl. Now let's create the second waypoint. Let's just set it as Luffy's ship. Let's right-click. Alright, let's open its 3D view. Next, I'll adjust the seabed and water depth a bit. Based on the topography of the Caribbean Sea, let's set the water depth to 200 meters in MOB. Then, to make the animation look better later on, let's also increase the width of the water surface so that the waves in the animation will look much wider. The width of the water surface will be very large, right, not the waves themselves. Alright, let's double-click on Blackpool. Select our Black Pearl file. Import our geometry model. Before importing the geometry model, I'll first adjust its position. Why adjust it first? Because after importing the geometry model, the mesh file is very large, and if we adjust it afterward, SIMA will lag, so we should make adjustments beforehand. You can follow along and input this with me. Let's scale up the model a bit. When it was originally modeled, the size was relatively small. Alright, next let's select the geometry model file. Import it. Okay everyone, take a look at our model. When I first started making this video, the leader from the association said it couldn't be too playful, so I modified the model a bit. Originally there was a skull flag on top, but I toned it down. It turned into a black and white tic-tac-toe board. The leader from the association said this is a scientific research video. It can't be too playful. Next, let's double-click the second package point. Import Luffy's Going Merry geometry file. Now for the rotation at position 9, let's change it to 90. Adjust the generation multiplier. Alright, now Luffy's ship has also been imported. Next, let's hide the combined body first. Because the combined file is a bit large, it might affect the operation. Next, let's add one to each body respectively. Connection. Why do we need to add it? I already explained this in the previous video. Then let's create a new Sofin load. First, let's create the first Sofin load. Here, we enter 100, assuming the length of the cable is 100, which means the distance between the Black Pearl and the Going Merry is 100 meters. A 10s serves as the motion reference point for the Black Pearl. Next, create the second motion reference point, which is for the Going Merry. As for Luffy's ship, let's set its supernode to free. Alright, let's keep the island at the origin. Next, we select the Sofin node we just created. The purpose of this step is to set your supernode as the connection for your body. Okay, let's take a look at the 3D view. You can see that these 2 points are now the motion reference points for the 2 floating bodies. Let's turn on the geometric model. You can see that the black sky pig is towing Luffy's ship behind it. Alright, next we're going to create a new one. A cross-section for the tow rope, which is the core section of the towing cable. Here, we need to enter the parameters for the towing cable, such as its weight per unit length and cross-sectional area. Then, let's rename the cable. Oh, right. Also, we need to enter its axial stiffness. Since the pirate's rope is quite strong, we'll enter a value accordingly. Okay. Next, in the line type panel, we select the cross-section we just created. Set the length to 100. That is, the length of the cable. Alright, next we can go ahead and create 2 endpoints for the cable. Let's name one endpoint HS1. That is the end on the black pearl. Set it as the slave. The master is the motion reference point of the black pearl. Alright, next, let's create the second one. Some people might ask, since this point overlaps with the motion reference point of the black pearl, does it matter? Actually, it doesn't. If the positions of the 2 Suhono points overlap, it doesn't affect their movement. In other words, they can overlap. Alright, next, let's create a new line, which is the cable. In the line section, we select the newly created line type. There are 2 endpoints. Okay, with this, the cable has been created. We can take a look at the 3-view diagram. After creating the cable, we need to add hydrodynamic coefficients to the 2 attached bodies, which means importing the G1.saf file. We select the interface file. Alright, select the G1 file. Open it and import G1. Then under the G1 body, find the hydrodynamic coefficients folder. Copy it. Simply paste it directly into the specific folder located right under the black pearl body. Alright, next, let's import it. The G1 file for Luffy's ship. Of course, this G1 file isn't just randomly chosen. For example, if you want to do it like I did. In G&E, model this ship. For example, I modeled the black pearl in Gian. Then, you need to first generate the wetted surface. After generating the surface mesh, we need to perform translation analysis in hydro-D. If you have the capability, you can also share the results of the translation analysis with Captain Jack. Alright, let's return to CMA. After building this cable, the dynamic fine hammer is brought in, and then we proceed to analysis settings. In the static analysis, we increase the end step value a bit. That is, we set a larger static iteration step size. Because this involves 2 anchor points, and there is also a cable in between. Change the simulation time to 2000 seconds, and also set this below to 2000. Then, go and change the motion reference point of the black pearl needs to be released at the beginning, set to free. Next, we select the option for storage, to successfully export and save the animation. For example, for the animation duration, I can make it a bit longer. Alright, now we can take a look at the 3D model. Next, since the black pearl has no power, it's a sailboat driven by the wind. If we want to simulate a sailboat in C code, it might be quite complicated, so we'll use a simplified method and directly apply a force to the black pearl to represent the thrust from the wind. Right-click. Select to add a specific force. Alright, over here. We see this setting, set the force. Set the magnitude of the force, just give it a random value for now. As long as it can move, that's fine. Change the direction to the positive X direction. Here is the start time of the force, and here is the end time of the force. You can see that this value is very large. That's because I want this force to remain throughout the entire simulation process. Alright, with this, we can proceed with the dynamic analysis. This is one of our working conditions. A working condition in the Caribbean Sea. Alright, once again, select and start the dynamic analysis. If the model and the hydrodynamic coefficients are correct and the settings are fine, SIMA will not report any errors. Let's take a look. Alright, there shouldn't be any errors. Okay, the run is complete. We can take a look first at the results of the analysis. Because this ship is always moving in one direction, its pitch curve is basically a straight line. Let's take another look at the heave results. Alright, next let's take a look at the animation. Okay, let's play it. We can see that the legendary Black Pearl is steadily towing Luffy's iconic Going Merry forward. Of course, the shapes of these two ships won't affect your simulation results because in the SIMA software, the geometry files of the models are just for making the animation look good. They are not involved in the calculations. If what's being towed is a semi-submersible platform or a floating wind turbine, the simulation process is the same, only the hydrodynamic coefficients are different. As you can see, when the movement starts, the towing cable goes from being bent to straightening out. In this state, the ship at the back, the Going Merry, does not move. This is closer to the real situation. Of course, this animation can also be saved. For example, if I want to calculate and observe the force on the towing cable right at its midpoint, After that, we will be able to. Currently, in the dynamic analysis data, we only have the motion results. For example, this is the heave motion. If we want to see the axial force results of the cable, we can element. In Lee's selection here, we select this line, Alright, let's rerun the dynamic analysis. At this point, you can see. Now you can see the result of the axial force on the towing cable. Of course, the current towing model is relatively simple. There is also only one towing cable. If there are two ships or a towing method composed of different cables, that can also be simulated. Alright, that's it for today's lesson. Next, let me give you a preview. In the next video, I plan to explain lifting operations. For example, if there is a swimmer in the sea, a sunken ship, a heavy object, or even a Godzilla, how do we use another ship to lift it up? First lift it up, then put it down. How do we simulate such a process, especially considering wind, waves, and currents? Alright, that's the end of this video. Thank you.